Hello, everyone. Welcome to this Windpower Engineering and Development webinar, Increase Your AEP, or Annual Energy Production, with Wind Vortex Generators. I'm your host, Michelle Rose, Senior Editor of Windpower Engineering and Development magazine. Thank you so much for joining us. Just before we begin, I'll quickly get over a few housekeeping items. At the bottom of your audience console, you'll see several application widgets for your use that you can move to suit your preference. For example, you can click and expand the Q&A one, and this is where you can type your questions during the webcast. I'd suggest not waiting until the end of the presentation, however. Type your questions in as they come to you, and we'll try to answer as many as possible before our time is up. If we run out of time or the question calls for a fuller response, it will be answered later by email. A copy of today's slide deck and additional materials are available in the resource folder, initially at the bottom of your screen. If you have difficulty, please click on the Help widget, the one with the question mark icon. Information there covers technical issues. And as not everyone who wanted to attend today's webinar could be here, you could help them learn from it by tweeting key points and the takeaways that you think are important. There is a place to tweet on your desktop, and just be sure to include the hashtag WindWebinar. An on-demand version of the webcast will also be available a day or two after the live presentation, and it can be accessed using the same audience link that was sent to you earlier. Now let me tell you a little bit about our speakers. Today you'll hear from Customer Account Manager Charles Kasmer, who manages the relationship between the EDF Renewable Services O&M Services team and EDF Renewable Energy Asset Managers. He's been in the wind industry since 2008. Prior to EDF, he spent 8 years with GE Renewables, where he held multiple different roles, most notably managing the operations of a 490 megawatt wind project. Charles holds a Bachelor of Applied Science in Energy Management from Bismarck State College. You'll also hear from Santosh Chandrabalan, the global head of 3M's Wind Energy Group. He has a degree in Composite Material Engineering and Engineering Management. Santosh has been in the composites and wind industry for his full career, and his experience includes research in composites, process engineering, and engineering management in the wind industry. So thanks for your time today, gentlemen. Charles, I believe you're going to get us started, so I'll hand over the controls to you.
Thank you, Michelle, for the introduction and the kind words. Santosh, also, thank you for helping me host this webinar today. Welcome to the EDF and 3M joint webinar. Today's topic is increasing your AEP with Wind Vortex Generators from 3M. EDF has partnered with 3M and SmartBlade to provide a superior VG offering to the market. EDF is a leading ISP in the industry, providing highly trained technicians to install the VGs. This is coupled with superior VG material and adhesive compound that 3M has developed with their decades of experience. Rounding out our partnership is SmartBlade, who has a design engineering and performance validation of the VG product. So what is annual energy production? AEP is the amount of electricity a wind turbine generator produces over 1 year. What can be your major impacts to AEP? One can be major component failures, being gearbox failures, blade failures. This can lead to long-term downtime. We also have blade damage and blade erosion, which can reduce the performance of your wind turbine. Then we also have grid curtailments, which are completely outside of the control of the site. So let's talk a little bit more about AEP and why it's a priority. Why are we focusing on AEP? Currently, sites have access to government-funded production tax credits. The government is phasing out the PTC over the next 3 years. This year, we see a 20% reduction. In 2018, we see a 40% reduction. And in 2019, we see a 60% reduction. We want to ensure that we are maximizing our megawatt generation to increase the site revenue and capitalize on as many production tax credits during the first 10 years of operation. You may ask, why do sites have difficulty meeting generation forecasts? One reason is the PTC. Over time, the government has phased it in and out, and this has caused, in some cases, development of wind farms to be fast-tracked. Within that fast track, sometimes we don't do proper resource assessment. This can also lead to, in rare cases, incorrect turbine selection and incorrect turbine placement. We have also seen that with some turbines, and especially new platforms, they are not meeting their power curve. Our big takeaway is that in the next few years it is critical to maximize the site revenue by increasing AEP. So you may ask, how do we enhance AEP? Well, we have a couple options. We have pitch optimization, which a lot of OEMs are doing right now. They're going in and adjusting our pitch parameters. We also have yaw optimization, which is correcting the yaw offset of the tower. And then we have blade aerodynamic optimizations, which can be VGs like we're talking about today. They can also be blade spoilers and trailing edge serrations. And lastly, we have major component hardware upgrades, which can be repowering, which is very popular right now. We can also have converter upgrades, blade extensions, and drivetrain upgrades. At this point, I would like to hand it over to Santosh to talk about blade aerodynamics. Santosh?
Charles, thank you so much for the transfer here and also having me participate in the webinar. This is a great opportunity for us to look at this industry problem and see how we can drive more efficiency to our customers and, more importantly, to the industry to push wind growth even further. Now, with that said, you kind of outlined some of the major challenges as an industry with respect to the tax credit and to be the need for being efficient and taking every ounce of power that we can get from the existing turbines. Now, you also mentioned about the aerodynamic challenges. So first, let's look at what is the challenge from an aerodynamic standpoint. Why do we need aerodynamic attachments in this space is the first thing to look at it overall. While we have a lot of growth in the technologies in a wind turbine, wind blade, which is pretty much the motor of the rotor, trying to, as we know, contributes the most amount of power related to the wind speeds, there is always a constant give and take away from an aerodynamic standpoint versus structure standpoint, and then how do you really install the turbine. So there's always this compromise that the aerodynamic team versus the installation team versus the structure of it, how do you really build a blade. If you look at an optimum blade just from an aerodynamic standpoint, it will almost resemble the one on the right here in this slide, which resembles very close to a wing of an airplane blade. But in reality, we know that we don't have such big chord options on a wind turbine. In order to be able to transport and attach to the turbine itself, we have the circular route. So that's one of our first challenges. So the root of the blade is not aerodynamically optimized, so there's a potential for us to gain some energy from there. The second aspect of it is the limited blade twist. In theory, we would like to have a lot of blade twist to optimize the aerodynamic performance. However, we are limited again by a lot of factors in terms of transportation, installation, and operational flexibility and so forth. As a combination of these two, there's a potential for us to have external attachments to optimize the aerodynamic portion of the blade, which in turn will help us to increase the power output. So that's kind of what we are going to learn a little bit more about this in this webinar and then see how we can really correct. So what's happening because of this aerodynamic deficiencies? Because of this aerodynamic deficiency, you actually see the laminar flow or the boundary layer being detached and actually causing reduction in lift due to stall that's happening. So that's shown in the picture here. Because of the stall, we are actually losing some power, which could be, again, used to increase the annual energy production. So that's one of the key challenges. If we can fix, we would be able to address it. And beyond that, the normal wear and tear of the blades, it's also very important for us to understand when we are trying to harness every ounce of power, it is important to make sure, one, we optimize the blade itself, but more importantly, we even preserve the shape of the blade as it's intended to be. Many times we focus on these upgrades and try to get more power of it, and then sometimes we forget as an industry to maintain the blade, first of all, to its optimum shape or aerodynamic structure. So there's also studies showing that aerodynamic impact due to the erosion can lead to up to 20% loss in energy. While we try to get every ounce of energy, sometimes we forget this degradation as well. So that's another aspect of it that we need to focus on as well before we learn more about the aerodynamic attachment. So if your team is looking to install or upgrade, make sure the current turbine is optimum. And that's one of the things I think EDF has great experience in resolving those kind of challenges as well. So with that said, we spoke about stall. We wanted to understand what is actually happening in there. With this constant stall, you can have beyond aerodynamic impacts, and you can actually have other loads which can cause long-term problems to your turbine as well. So it's important for you to understand what kind of loads are happening. It's also important for you to understand how can we really resolve that problem of moving forward. So other factors because of the aerodynamic deficiency is when you have the boundary layer flow separated, it can lead to noises due to stall. So many times this is a big problem in the industry, especially if you have turbines very close to a residential area. And many times we see this in Europe where a big challenge is noise. And many times we actually focus on adding attachments to just address the noise, but sometimes correcting the aerodynamic flow alone can even increase the noise. This is a concept of energy can never be created, right? So it can be conserved or transferred. So when there is noise, you have a loss in energy. That's what we are trying to capture back as well in terms of increasing power. Now, with that said, what we are looking at moving forward is how can we influence those factors? How do we increase that power, especially in the deficiency caused in the root area, and what can we harness from that point is what we're going to understand how we can fix that. So the solution, how do we know, what do we do? The solution is, one of the solutions is the vortex generators. So what is a vortex generator? I think most people in the call already knows it, but just to recap, vortex generators actually is an improvement device to redirect the flow and delay the stall, or to be able to optimize your aerodynamic profile of the blade by reducing the separation. So the vortex generators has been in the market for a very, very long time, in aerospace industries and many aspects of it. However, there are some challenges that needs to be solved from an industry standpoint for it to be very effective for us. So what does vortex generator do is vortex generator enhances the mixing of the outer flow. So when the wind comes and hits it, it creates controlled turbulences to reattach the separated flow, that re-energizing the surface, getting more lift, then in turn more power as well. So that's one of the key aspects for us. Again, the basic understanding of vortex generator has been in there for a very, very long time. However, from an execution standpoint, we've always had challenges. And with this partnership, we are able to actually have an effective solution that lasts much longer as well, which we learn a little bit more. At this point, I'll turn it over back to you, Charles, and then we can continue the discussion here.
Thank you, Santosh. Sorry. So why are we installing vortex generators? The main reason is because they work. Vortex generators are not new technology. The aerospace industry has been installing VGs on airplanes for decades. The use of VG to increase the lift on wings. Recently, you have started to see automobiles come out with VGs. I actually have a coworker who has VGs on his vehicle. And because VGs are not a new technology, many of the turbine OEM and the blade OEMs are offering VGs from the factory because it is a proven technology. Sometimes they are offering them to meet the power curve. Other times they are offering them as a performance enhancement. The main reason is because VGs are a proven technology that should be used to maximize the turbine's performance and maximize the output. So why don't all turbines have VGs if we know it's a proven technology? Well, there's some concerns out in the industry about VGs. We've had some problems. One of the problems with VGs is they fall off. It is one of the leading issues with VGs in the industry because of adhesion. When VGs fall off, we have quite a few issues. One, we have an environmental concern from the VGs falling off, going into fields, going into wheat fields, corn fields, possible animals eating the VG. We also have a safety concern because we have people out at these turbines. We have technicians that are going out to maintenance them. We have landowners that may be walking underneath them. We don't want to put those people at risk from a falling VG. This is why we utilize 3M's VG, because they have successfully installed these VGs on thousands of turbines. Another thing to take into account is the cost. When the VG falls off, that means we have additional cost. For one, we have a reduction in AEP that we were forecasting. We also have the cost to reinstall. That is the material and labor cost to go back out to the turbine and put the VGs back on. We also have more downtime. We have more time that turbine is not producing energy. This is why we have partnered with 3M, as they have a robust product that adheres to the blade, and it is partnered with EDF's streamlined installation process to reduce the owner's cost. Lastly, if you're going to install a AEP enhancement, you have some costs there, and you have to forecast that AEP increase into your model. This has been an issue in the past, where some owners have not been able to properly forecast the AEP improvement, so they can't go out and make these purchases. This is why we have partnered with SmartBlade. They bring their industry-accepted power versus power methodology to the table. This allows our customers to forecast their AEP increase and make smart decisions. At this point, Santosh, I hand it back to you.
Thanks again, Charles. You pointed out some of the major challenges in the industry and the technology because of that. One of the first things that happens is, as you pointed out, the longevity of the solution is very important. The other aspect of it when we look at vortex generator is the positioning of it. So that's the first problem, right? To see where to put these vortex generator, how do you really design that? And when we look at many of the solutions in the market, they're all based out of models in a computer rather than actual blade designs. What happens is we know such a large part from the design in a computer to the final mold part that comes out of it has a lot of variations. So when we looked at this problem to solve with our partners to say, how do you really resolve this problem, we actually had an ability to come up with a method to understand the blade flow in operation. Rather than focusing on working out of a model, we are now able to actually understand the flow of the wind right on the blade surface and understand where the deficiency or the flow separation happens and then go fix it. This makes it very accurate. So that's the first thing for us to understand where to actually fix it can give us the most amount of optimum solution. So for that, we do something called smart visualization, which basically will help us to understand the flow by attaching different flow tufts all through the blade and using multiple different optics, wind measurements, and complex algorithms, we can really look and understand where the flow separation is happening. By doing this thorough analysis on an operating turbine, we can actually completely figure out what is the best position to install the vortex generator to a particular turbine and the blade model. That helps us to differentiate and make sure that we have the best efficient output from an VG installation. So by physically putting these flow tufts and by monitoring it, how it behaves, and using a complex algorithm, we can actually get an output, something that looks like that, which can take all the mean flow streamlines and then compile it into the results. And we have done this in partnership with TU Berlin as well. And the output of it can help us to understand where actually the flow separation is happening and what is the best method to do it. But again, with respect to different wind speeds, wind winds, all that, your flow separation can change. So we need to actually optimize on where to install so that you get the most out of your vortex generator installation. So that can really help us to differentiate from an installation standpoint. Second, now you know where to install, and then you need a material that actually is going to withstand the very tough scenarios for vortex generators, and it needs to be installed correctly. So this is where 3M comes into play from a material science standpoint. Vortex generator, as you mentioned, Charles, has been there for a very long time. The problem, especially in wind, is they didn't last very long. You installed it, and then in a few months, it fell off and becomes a problem. Even in an aerospace industry, it's a little easier problem because airplane lands, so you can go and fix it. Unfortunately, and hopefully, our blades don't land on the ground, so that it becomes much more expensive for us to go fix and address that overall. So when we looked at different technologies and how to really install a VG that will last long, so you have a return on investment for the money that you spend and make sure that you get more, we were able to come up with a proven technology. The first thing is you need a vortex generator that doesn't age very quickly. So you need to select the right materials that will actually last long. So our weathering capabilities that we have over many years really helped us to figure out which is the right material for this application. The second aspect of it is you need to understand how do you attach it. Most time, even when we started looking at this industry and see how do we fix this problem, we started with adhesives. We started with different adhesives to say how do we optimize the application and how do we extend the life of the vortex generator. And we quickly learned that the stronger the adhesive you apply, you actually have a lot of challenges or in fatigue. Why is that? When you look at a blade, our blade has a lot of flex. And also, our blade has surface tension because of the stresses and because of the flexes. To make things more complicated, you have a composite surface, again, epoxy or polyester, carbon fiber versus glass fiber. So you have a lot of different, coefficient thermal expansion on a blade itself, and then you have the surface forces. Then you apply a vortex generator. Generally, it's a thermoplastic or metal, depending upon what they are doing. That has its own coefficient of thermal expansion. So you have two materials that are, again, a metric ton to a few milligrams in weight, all expanding at different rates, going through the severe amount of weathering, heat cycles, cold, wind, rain, and all that. Then when you go to an adhesive that is rigid, there's no transfer of energy from the blade overall. So you have two coefficients of thermal expansion completely different, and you put a rigid adhesive in between, then basically the easiest part gives up because you need some flexibility, you need some forgiveness in this attachment so those forces are absorbed and not transferred completely. So this is where we decided to go to our acrylic foam tapes. So the acrylic foam tapes are high shear adhesive tapes with a very strong foam closed cell core, which gives the flexibility that you need for these different conditions and also the coefficient thermal expansion, compiled with the strength that you need for it to withstand very high forces and changing weather and so forth. that's the key for us to be able to solve one of the big challenges in terms of what we can do in terms of fixing a solution that will last long. So over the last few years, this technology is used in many, many turbines and thousands of turbines, and we see tremendous success on this long term, which has helped us to be, solve one of the industry's big challenges. Now that you have this two problems that we've addressed. One is the aerodynamic understanding, where do you really put it? Next is actually an understanding of what material that can last. So now it's important to see this in action. So this one slide or one picture comparison shows a very good understanding of what we are doing in just a few pictures here. Now on the left-hand side, you can see a wind blade. It's actually operational. And you can see these flow tufts that we were talking about a little bit earlier and understanding how the flow is happening, where the separation is taking place, and so forth. If you pay attention to the leading edge, the wind flow tufts is basically a bunch of threads joined together, if you may, is aligned to the wind direction or perpendicular to the blade length. Now, as we move forward, you can see the flow tufts are basically in parallel to the blade direction and perpendicular to the wind direction. So that's a problem. That means there's something happening where the flow is not attached to the blade. In turn, there's a flow separation, in turn causing stall, final output loss in AEP. So this is what we are trying to correct. So once we have this understanding, now that we know where to actually install with our complex model that we have, with that, now if you go ahead and install the vortex generator, the after effect, you can see very evident from the left to the right picture, you see the flow direction of these flow tufts are now in parallel to the wind. That's showing that the flow is reattached to the surface, thus increasing your power output. So this is a visual proof of the vortex generator actually working. This improvement of the flow being reattached in there can give you the performance increase that you're looking for from a vortex generator. So these are the two major problems that we were able to solve. Once we get to that, the third, not the least, but one of the key important aspects from this point is after you have an understanding of where to install, after you have the best materials to install, now the key factor comes into play of how and who installs it. Because while the science is right, if the execution is not good, then there's no progress in there or a solution that's effective. So with that said, I'll turn it over to you, Charles, for you to continue to say how do we really work together to get the best out of this installation.
Thank you very much, Santosh. So let's take a little bit of time to talk about vortex generator installation. How do we do it? I actually had the opportunity a few weeks ago to go out to one of our sites and watch our teams install VGs utilizing rope access. That's actually where this picture comes from. So as Santosh says, we do a SMARTviz on each turbine model to ensure that we have the optimal placement of those VGs. Currently, we have the ability to install VGs on 20-plus turbine models. And for each of those turbine models, we have a blade-specific installation pattern that we use. And our technicians are trained with the help of our internal trainers, SmartBlade, and 3M to ensure that they are trained up on each blade-specific installation pattern. We also have the ability to tailor our installations to the site. In some sites, it may make sense to do rope access. Some sites, it may make sense to do boom truck installation. It all depends on the site. What all this leads to is minimum downtime for the customer. We have seen between 8 to 10 hours to perform this installation, and at the end of the installation, we can put your turbine back online. If you look at this picture, you see the template. That's how we ensure that we have a precise installation. For every different turbine model, we have a different template that our teams use. And when we're doing rope access installation, we actually have two rope access technicians working on the blade. One starts at the root, and one starts down by the tip, and they meet in the middle. and they work in conjunction to install the VGs to ensure that we're following that specific installation pattern. So let's talk a little bit about results, the actual AEP increase. Customers can expect to see with the 3M VG a 1.5 to 3% increase in AEP. And when we're looking at wind speed locations, for low wind speed locations, you're looking to see upwards of 3%. And the reason that you see a higher percent for the low wind speed locations is because usually our blades are fully pitched into the wind and we are capturing the maximum amount of power. When we look at high wind speed locations, we're looking at the 1.5% range. And the reason for that is because when we get into those higher wind speeds, the turbines start to pitch out to capture less wind. So at that moment, the VGs have less effect. What does all this mean? It means that our customers are looking at a payback period of approximately 1 to 2 years. This includes the installation cost, the material, and the downtime for that installation. So as we talked about, we have 20 plus turbines modeled. And this graph right here gives you a taste of some of the turbines that we have profiled with the AEP gains. As you can see, the AEP gains are all over the place. This is because each turbine and each blade has a different air profile. Some are better than others. Because of that, we see different AEP increases. So in conclusion, EDF offers a turnkey solution designed for high reliability and fast rollout for our customers. EDF is working to increase customer AEP, which in turn increases revenue and increases the blade aerodynamic performance. These results are backed by customer data of actual performance improvement. And lastly, EDF offers a comprehensive installation package to minimize downtime. We also offer the ability to maximize that downtime by doing leading edge protection installation along with blade repairs. Because to maximize your AEP increase from VGs, you need your blade in the best condition as possible. Joe, I'll turn it over to you for a Q&A.
Sounds great. Thanks for the informative presentation, Santosh and Charles. Thank you. Yes, next let's take some questions from the audience. First up, I have a question about warranties and if you offer any for the Vortex generators that you install.
Yes, EDF does offer a 1-year workmanship warranty on our VG installation.
Perfect, thanks. You also mentioned the installation time, but is it important to install VGs on every turbine at a site to be effective?
I'll take that one, Santosh. Yes, it is, because you want to maximize the AEP of each individual turbine. So you would want to, if you're looking at maximizing the site as a whole, installing VGs on every single turbine at site.
That makes sense. Thanks, Charles. Next, I have a question about retrofits. And is the cost of retrofitting significantly less if the blade is already on the ground? Robert mentions that they're doing a gearbox change out and they have that scheduled. And we're considering adding VGs at that time. And does that make sense to do it that way?
Yes, when you're looking at installing VGs on the ground, you are going to have some reduced cost. The labor is going to be much less because you're not climbing the turbine. Also, you're not going to have the downtime because you're already taking the turbine down for a different repair. So you're maximizing your downtime.
Great. What about in different weather conditions, such as in icing? or any kind of storms, how do VGs hold up then?
Santosh, would you like to answer that question?
Yes, I can go ahead and take it. So that's a very interesting question. So when it comes to vortex generators or any of our turbines on the whole, right, they are not designed for very tough, unforeseen conditions such as lightning or icing. So when it comes to severe icing, there will be challenges to the vortex generator, so you need to be cautious about that. However, if there is actually even a failure due to loss of a vortex generator, the model is designed to such that you can even lose a few vortex generators without having any impact or any negative impact to your turbines. After a certain threshold, you are supposed to be able to fix it. And now, given that we have these independent vortex generator with the templates, we can actually easily go ahead and fix it on a very easy manner. One of the other advantages of the acrylic foam tapes that we've been doing and the way the vortex generators are designed is it'll be a clean break when it comes to severe icing. So now we can actually remove the acrylic foam tape. There are some specific tools and training that we have in place to be able to remove it and then put new ones. So while the vortex generators last very long, when in severe conditions, there's actually a good plan and an understanding of what happens and how to resolve it without having a major cost of that.
Thanks, Santosh. Philip asked, what is the resulting sound impact post-installation? Is it increased or reduced?
I can go ahead and take it, Santosh here. So with respect to after the installation, the sound should reduce on any vortex generators when installed correctly. So on a general technology standpoint, as we spoke about, when there is actually an energy savings, then that's where you have noise reduction. When there is noise, your energy is being lost. So with the analysis that we have done, and by installing the vortex generators to optimize the performance, your noise will be reduced, not increased.
Excellent. And do you offer tip VGs?
That's a very good question. Again, Santosh, I can take this as well. The tip vortex generators are a big solution that's been discussed for a long time. The challenge with the tip vortex generators is when you are at the tip, you have very high tip speeds as the blade is spinning. Now, any vortex generator can create a lot of load that can be well beyond the specification of the blade or the design of the blade. So we do not offer any tip vortex generators for that reason. Without understanding the loads of the blade, that is actually a very dangerous thing to do. So does many other aerodynamic attachments at the tip. If it's not understood properly, you have a problem. However, the root vortex generators, when you're installing, are designed such that it's well within the load factors and you have very little to no risk.
That makes sense. Thanks, Santosh. Another question for you. How much operational time is needed for the SMARTviz analysis? And is data available on demand, or how does that work exactly?
Charles, would you like me to take that too?
Yes, please.
Yeah. So with respect to the SMARTviz analysis, so we have actually profiled more than 20 plus turbines. So we have a good understanding of different turbines and blade models on how it actually the performance is and where the vortex generator needs. So that actually covers a very good population of the installed turbines. However, if you have a turbine that is not flow visualized, we do need to flow visualize the turbine, and that depends upon, again, the turbine and how long it'll take to do that. So generally, we should be able to, if it's all scheduled, the whole flow visualization is a few days, depending upon weather, like 2 to 3 days, you should be able to be completed. So it's just the planning process and getting to it. But the whole flow visualization, your downtime is very less. It's just you're going to put the flow tabs and then understand how the flow visualization for a day or two to understand where your flow separation is. So it's not a long process, but it is something that needs to be done on new unflow visualized turbines.
And back to the VG specifically, how many wind vortex generators can fall off before turbine production is affected?
It can also depend a little bit on the blade and turbine. So generally up to 10% of it is okay. It's designed into the factors. In some cases, we can even have more leeway. So it slightly depends upon the turbine and also the blade.
Thank you, Santosh. I've got one last question for you. I imagine this varies, but how long do VGs tend to last over time? And have you experienced any major failures?
That's a great question, and that's $1 million question, right? How long anything lasts overall. So we tend to understand that we now have vortex generators with this technology installed more than 5 years, I would say 4 to 5 years. With the only time the failures have we seen is for severe icing or lightning strike. Other than that, we have never seen a vortex generator fall. So with that said, minimum 5 years should be very possible. The same technology is used to bond like the plates that you see in your road signs. It is used to bond cars. It is used in solar panels for attaching as well. And they all have more than 20-plus year life cycle. So with that said, if in a given condition, possibly the vortex generator can last 10-plus years or even up to the lifetime of a turbine, but it all depends upon what other factors contribute to it. But with that said, it is important that it's installed correctly, and that's where teams like EDF has the best knowledge and training to properly install so you get the most life off your vortex generator.
Excellent. Thanks so much for your insight, Santosh and Charles. We are at the end of our allotted time, ladies and gentlemen. Once again, this webcast will be available for reviewing at windpowerengineering.com. One final message, you can follow Windpower Engineering on Facebook, Twitter, and LinkedIn. I'd like to thank Charles and Santosh again for their insightful presentations and everyone else for their attention. From the staff here at Windpower Engineering and Development and for the teams at EDF Renewable Services and 3M's Wind Division, we wish you all a good and productive day. Thank you.
Thank you, Michelle, and thanks for the team.
Thank you, everyone, for joining.